I am Deborah Wymore, the co-president of the Woodlands Green, along with Kathy Herrick. And we are live from the Artesian Culture Coffee Shop this evening, where there's a half dozen of us clustered and looking at a big screen and looking at Paul Lundy right now. So welcome everyone tonight. You're in for a real treat with a presentation on geothermal. And Carolyn's going to give background on the speakers. And we also have on hand for questions, Derek Adams is here at the coffee shop with us. Paul Nelson will help with the chat. And I think we've got John Geiger, another director. I can't see everyone that is present on Zoom this evening, but we have a number of directors with the Green. Later in the session, Paul will go over what's coming up for November in the next Going Green lecture. So with that, I'm going to turn it over to Carolyn to talk about our speakers.
Hello, everybody. I know you can't see me, or at least I don't think you can. So you're going to have to keep an eye on Paul Lundy. And let me tell you just a little bit about EarthBridge and our
We can see you.
Yeah.
Okay, good. Okay, great.
Just so you know.
All right. Technology is a challenge sometimes. So EarthBridge Energy is a geothermal startup, of which there are many in the Houston area and around the world. A whole lot of oil and gas professionals are recognizing that their skills are well suited to solve the technical issues around making use of geothermal. And also, so many of them understand the need for the planet to transition away from our dependency on petrochemicals, particularly for the energy, electricity, and transportation sectors. Before I introduce the speaker, I would like to say, just full disclosure, you'll find that I myself will be listed on the EarthBridge website as an advisor in the realm of community outreach. I received no compensation for this, and there has been no conversation or anticipation of any compensation. Also, the Woodlands Green is not endorsing EarthBridge. We are a 501c3 nonprofit, and part of our mission is environmental education, which is why we are having these guys educate and inform us about geothermal energy. We hope there will be lots of questions. So joining us today, we have three members of EarthBridge. Paul Lundy, who is our primary speaker, has over 30 years worldwide experience in the oil and gas industry in both technical and business management positions. He has extensive economic modeling and analysis experience and has given introductory courses to all levels, including to senior management. For those of you who are lucky enough to be here in person, you are so lucky to get to meet Derek Adams. He's here, and we're going to have quite a party afterwards. Derek is a PhD geologist and worked on large capital projects at ExxonMobil as a project manager and geoscientist. Derek likes to leverage his practical experience and wisdom to find innovative solutions to the world's current energy challenges. Sounds perfect. Let's do it. Gus Perez, I think Gus is also online. He is EarthBridge's finance guru with many years of corporate finance with oil and gas giants and other energy service companies. So with that, Paul Lundy, we'll ask you to share your screen.
Let me know when you see it. I think you have to do it, Carolyn.
I am working on it. Hang tight.
Says you disabled it.
Oh, well, not intentionally. Let's try a brand new share.
Nothing's been intentional. Just
Okay. Paul Lundy, can you look at it again? I've disabled my share.
Okay, hang on a second.
You're showing up on my screen.
Well, it doesn't seem to. Oh, come back up. No,
Not the presentation, no.
True. Thank you, Paul.
tell me when you can see something, please, because I don't seem to have any controls on Zoom. Well, I think you may have to do it your side here. I can't. I've lost the Zoom screen. Can you still hear me?
I can hear you, yes.
Right, it's not letting me. It's asking me if I want to leave the meeting. That's very helpful.
Can you hover over the bottom edge of your screen and see if some options will pop up?
Right at the bottom of the gray area, that's where they show up if you, I had trouble finding them too.
It's like the screen doesn't want to come back up now. I can.
Try it now.
Yeah.
You can see me? Should I do publish arrows?
If you want, I've got it up on my machine, if you give me permission to share.
Well, I'm trying to see,
He has permission.
Paul, Derek,
You want?
does Derek have permission?
He does. Oh, Derek, actually, I'll give it to him right now. There we go.
Okay, I think we're back.
Interesting.
And it says host disabled participant screen sharing.
I need to reassign it to you now that you're back.
Okay.
Let's see. Okay. There you go.
Okay. And I think you should see things now. Can you see it?
Yes.
Excellent. Well, it takes technology, doesn't it? Anyway, we'd like to thank Woodlands Green for inviting us here to present to you tonight. We're looking forward to it. I hope you learned something from it. We're very pleased to be able to share what we're doing with you. Please listen closely. I come from another country where we don't speak real English. So if you don't understand something, holler. I'm sure Derek will tell me. Here's a quick look at the agenda. Before we get into geothermal, we'll talk a little bit about where we are today, what the forecasts are for electricity usage, some impacts of using hydrocarbons, specifically coal. And we'll move into the renewables, discuss solar and wind a little bit, and why geothermal is a really good complementary power source for it. We'll talk about the different geothermal generation technologies, where they are at this moment, and why is it taking so long to develop this technology, and why is the interest with us now? And then we look at some of the advantages of geothermal, and we'll summarize at the end. During the presentation, I'll be asking you to participate a bit with questions. Just answer away. First of all, though, this is who you're looking at. You've already been introduced. And the dog is Caden, my dog. And after that, Derek and Gus now, I think we'll just elect him the CEO. He's the cleverest of all of us by far. Okay, firstly, though, there's a few definitions. We won't wait too long on this page, but we will be discussing lots of things. And the first thing we'll hear about a lot is a watt. What is a watt? You can read that the SI unit is 1 unit of power equivalent to 1 joule per second. Basically, 1 volt producing 1 amp gives you 1 joule. If we use 50 joules in 10 seconds, that's 5 watts of power. You've heard of kilowatts. The average Houston house uses about 1.6 kilowatts. A megawatt is 1,000 kilowatts or 1,000,000 watts. And that's somewhere like 600 to 700 average houses. That's the amount of electricity they use. Next one up, another 1,000,000 is gigawatts. And you probably remember, if you want to go back in time, you must use 1.21 gigawatts, which, as you may also recall, is the power in a lightning bolt. It's also about 1.3 million horses. So if you're standing in the street and 1.3 million horses are coming to trample you, they will trample you with 1 gigawatt. It's quite a lot. And another 1,000,000 is a terawatt. And that is actually more than the US uses every day. Other things you may hear is a kilowatt hour, forget that definition. If you use 1 kilowatt for 24 hours, you have used 24 kilowatt hours. Very simple. And a megawatt hour is about 1,000 of the above. In New York City uses around 11,000 megawatts daily, which is around 458 megawatts, 460. So quite a lot of power.
Display one.
So I understand that you can write questions in or answer back here, but I'd like to know, think about it. What has access to abundant energy done for us? Imagine what it would be like if you didn't have energy. Has anyone got any ideas? Anyone want to open up and say something? Silence is deafening. Let's give some clues. We live in the modern day in the world we live in, the modern day life. We rely so much on energy. Just about everything we do. Anyone uses the Xbox, you turn the TV on, you know, we're going to do the cooking, dishwasher. Think of what life would be like without energy, without jumping in the car to go down the road. Another thing to think about as we move on is, do you actually worry about leaving a light on when you go out? And if you don't, why not? Okay, guys, someone speak up. How much electrical energy does the US burn through every year? And as you go, A, 1,000,000 kilowatts, which is a gigawatt, 2 billion kilowatts,
Yes.
1,000 billion kilowatt hours, or 2 billion megawatt hours. What do you think? A, B, C, or D? Some people are on. Drew Richards says C. Gus says B. Anyone else?
C. Paul says C.
C. Let's have a look. Great. Yes.
Ray Hanley says D.
The answer is C. 4,000 billion kilowatt hours. It's a number so large, you really can't start putting your head around it. Texas, incidentally, uses about 10% of all that. Here's some comparisons worldwide. In 2018, the US spent about $1.3 trillion, 6.2% of GDP on energy. Less than 5% of the world's population. It consumes nearly 17% of the world's energy. China has caught up amazingly. They're now at 24%, but for 18% of the world's population. So per head, the US is still using around 2.5 times as much. And the EU with 7% uses 11% of energy rather. I keep saying electricity, it's all energy. And that's one of the reasons Europe's smaller towns, different travel distances, they do have smaller houses, smaller cars. They also have access to better transportation systems, and we'll talk about that soon. But bear that in mind, 4,000 billion kilowatt hours. And here we are. This is from the EIA, which is the Energy Information Authority. It's you can go on there, look it up in the EIA, go on their website, and you can find everything, how much coal is burned, how many people, matchsticks, anything that uses energy is on here, and forecast, oil, gas. And you can see here on the left, in 1950 to 2020, how the US has been increasing its electricity consumption around 2% per annum. until around 2000, 2005. And various things happened here. Energy efficiency improvement, a lot of heavy industry now being offshored. Notice the very bottom on the left, the brown, that's coal. And from around 2006 or 7, the use of coal is dropping off precipitously. What is increasing is natural gas and renewables. Later on, we'll see why that is, but it's very good that coal is reducing. And again, as we move on, you'll see exactly why. In terms of renewables, you see from 1950s, we've been using renewables, but a lot of that is hydroelectric. And by 1975, that has more or less leveled off. There isn't many more places you can dam the rivers up. In fact, for hydroelectric in Nevada, you probably know Lake Mead is something like 40% lower than it should be. And so a lot of the hydroelectric, which is in the west of the country, a lot of those lakes are now drying up, which could cause a lot of problems. But from 2000 onwards, we have seen a huge increase in wind and solar. Solar is increasing very fast now. Notice this little line here. There's a little orange smudge. That is geothermal, which has hardly changed. And we think it's about time that did change and increased. Looking to the future now, this is obviously from 2019, but the 4,000 billion kilowatt hours over the next 30 years looks to increase by around 30%, up to around 5.5 billion kilowatt hours. Natural gas will still have a large part of that, but renewables are forecast to double, with coal is going to reduce quite a lot. On the right here, you can really see where this is coming from. Most of the increase is going to be solar, and solar costs have dropped quite a lot. The thing about solar and wind, as we'll see later on, is that at night time, you don't get electricity from solar, and when the wind stops, you don't get electricity from wind. So this little smudge again in here, geothermal, meant to be about 3%. What I'm saying at the bottom here is the 17%, which is hydro and geothermal, they're base power, they're not all the time. And as 38% is forecast to be renewables, and only 17%, sorry, is forecast to be base, that means of all the renewables, only about 6% is what you would call reliable. And by reliable, I mean you can use them all the time. You may also be aware that the government has announced they want to achieve zero transmissions by 2050. And looking at this graph here on the left, can anyone tell me why that looks like it'd be very difficult? No one in chat? Why can't we? Look at the bottom of that graph. Still 13% coal. If you don't get rid of coal, you're in big trouble. And natural gas produces about 40% of the carbon coal does. The actual target, and we'll see in a minute, actually, the government would like for electricity generation is to be carbon neutral by 2035. Didn't want to move forward. There we go. So let's have a quick look here at what coal does for us. I mean, when they discovered that you could create electricity from boiling water and using the steam to drive turbines, coal was the primary source. And thanks to that, you know, our lifestyles have improved dramatically. It's quite obvious now, though, that what coal isn't doing for us is keeping our air clean enough to breathe. So it takes 1,100 pounds of coal to produce 1 megawatt of electricity. And what you do, you go and find your neighbour's sauna and you fill it out with it so you can take a picture. That's what it looks like. It contributes 2,100 pounds of carbon. And it's the same with gasoline. You always get more carbon than you burn in the weight of the power source because it combines with other molecules. It also produces some other rather nasty stuff. When I was a kid, we weren't overly concerned with climate change. We didn't hear about it, but we did know about acid rain. Sulfur dioxide, nearly 4 pounds, mixes with the water, falls on the trees and kills them. 13 milligrams of mercury. I'm sure you all know from your school days that touching mercury isn't the cleverest thing to do. So coal is a very dirty fuel. In fact, in 1 year, a 1,000 megawatt plant will create over 9 million metric tons of carbon. That's 2,200 pounds. A short ton is 2,000 pounds. That's nearly 10 million tons every year of carbon from one 1,000 megawatt plant. Gas would be about 40% of that, about 4 million tons. So you probably remember this graph here. Remember me saying why, although the government wants zero emissions, the EIA's forecast says you can't do it, because that amount of coal is over 500 million metric tons of CO2 annually, all the way from around 2025 to 2050, with no way it looks like they're ever stopping. My ambition would be, at the very least, let's get rid of coal generation. Worldwide, and this is actually as of July 2021, this is the number of operating coal plants. And you can see by far and away, China has the largest amount, followed by India. The US is, as you could have already seen, is actually reducing its amount of coal it's burning, which is a good thing. But China's economy has, it's let forward in leaps and bounds. And to power that, you need a lot of energy. And coal is something they have in abundance. Worldwide coal emissions, though, the US is actually just ahead of India, but China is about 4 times as much. That's about 9.4 thousand or 9.4 billion tons of carbon is emitted by coal power stations every year. And if you're not worried about that, you really should be. That isn't good. What we see on this map is where you get your power from in the USA. So up here, up in Oregon and Washington state, there's an awful lot of hydro, damming the Columbia River and things like that. A lot of these rivers, and they've been used for hydro. This little blue dot down here, I believe that's the Hoover Dam. And there's also a lot of hydro up here. Pennsylvania, Ohio, West Virginia, known coal countries, a lot of coal power stations there and all throughout this area. And also around here, Wyoming, Montana, a lot of coal is produced. Wind, you can see a large swathe of wind going right up through the country. And later on, I'll show you a map explaining why. Nuclear is dotted all over the place. And you can also see the main population centers where the power stations are, Houston being down here. So there's a lot of solar around here. It doesn't really appear on this map. And then there's 2 or 3 or 4 green dots here. There's a big one here. This is a very big geothermal plant in California, steam powered. It's a couple of dots here, and you see a few scattered around Nevada and Utah. Later on, I'll show you a map as to why you're seeing them in these areas. Well, there you go. This is where all your power generation comes from. The bigger the circle, the more powerful the power station, as you can see here. 20 million megawatt hours, for an example, for this station. So I'm going to give you a quick geography quiz. Stops me talking for a while. So for information, that's where I come from. At the end of that little dot is London. So I'm going to ask you questions. I'd like to know, what are they and where will you find them? Number 1, what is this and where is it?
Oh, I know.
Looks like the duty.
I know, I told you the other day, Carolyn.
Yes.
Everyone get on chats and tell me, what is that and where would you find it?
Looks like London.
We have an audience member who says it looks like London.
Yep.
The tubes.
That's right. That is London. And Squib has said the tube is right. Mark Stem, DC, I'm sorry you're wrong. It's London. Go. How about this one? I'll give you a clue. If you dangle your feet in that river, you're insane.
So that will be-
That's right, Jeanette has replied. Paris. It's the Paris Metro. A bit closer to home.
New York.
New York City. Correct. And finally, this one.
Real close to home.
Real close to home. Come on, people, type out. Where do you find this?
Like Houston's, one track going nowhere.
Absolutely right. That is Houston Metro. Here's a map of London. Okay, let me just show a couple of things. I used to live here. I could walk to here, get a train down to here, and I worked here. I could get a bus or I could walk. My sister now lives here. You walk to here, you get a train into town. This is about 25 miles from here to here. London actually goes around here, not this bit. It's about 20 miles there to there. So it's very easy to get on a bus or walk to the station. Houston, on the other hand, we're all up here. I'm almost off the map. I'm down here. Gus lives around here. From here to here is about 25, 30 miles. And if I have to drive that far, I'm really not getting this. It's called a last mile problem. It doesn't really take you anywhere. It's very nice, but it doesn't really take you anywhere. And before I move on, incidentally, do you know the city in the US which has the longest mileage in light rail?
Dallas,
Dallas.
Dallas, that's
A lot for my daughter's fiance lived there, and the train went by past his apartment about every 5 minutes and no one was on it. So why don't people travel by train? Very simple. There isn't one to catch. This is another reason Europe has lower energy use. They have very good public transport systems. And unless you live in a place like New York, Washington, then it's very hard to do anything else. Even the buses don't come out to where I live. So we have some generation challenges. Let me just say a couple of things here. The first thing is that the federal government wants to reduce emissions by 50% by 2030. That's just over 8 years. And that's compared to 2005 levels. They also state they'd like to produce carbon-free electricity by 2035 and be totally carbon neutral in the whole country for 2050. That's less than 30 years. One of the things they'd like to do is by 2030, all car sales should be EVs, electric vehicles, Teslas. And you've probably seen GM and Ford have announced billions of dollars in funds to go and make more electric vehicles. Now, you'll come home at 6 o'clock at night and you plug in your Tesla, you could have a bit of a problem. Right now, the forecast from the EIA is we'll end up around here by 2050. But if America is to aggressively electrify to meet the transport issues or the transport forecasts or wishes, if you like, also power its buildings by electricity and not gas. You may have heard in California, some places they're regulating you can't cook with gas anymore. New houses have to be electric. Heavy industry, electrify it. Your forecast goes from around 5.5 billion terawatt hours to 7.5. And it's no use taking gasoline vehicles off the road if you're going to transfer the electrical generation problem somewhere else. You see, the thing about Houston is realistically, it looks like this. There's a lot of car owners, limited public transport. And if all these people here were to turn to electric vehicles and come home at 6 o'clock at night, and we generate the power by coal, you've increased the problems. Because for about every kilowatt you burn at the house, a coal, gas or nuclear station has to burn around 2.5 kilowatts because they're not 100% efficient. And just for information there, you look a bit on the left there, every gallon of gasoline burned creates 8,887 grams of CO2. That's a very good measurement. That's about 20 pounds. So you drive off and you burn 10 gallons on average. You've burnt about, only work it out, 200 pounds of CO2. So we really must try and clean up the transport sector. And electric vehicles is one way forward, but we can't transfer the problem from the car itself to the power station. The fact you might not see the power station is neither here nor there. Wind will blow it towards you. Which is leading us on now to renewables. And what you're looking at here is quite a big solar farm. It's interesting how big these things are. That's a truck. This is like an 18-wheeler truck here. There's some switching gear. There's another vehicle there. These things are quite large. And yes, when they're actually operating, they do create clean electricity. Of course, you have to make them, you have to transport them, you have to cut down half the country to put them in. But when they're making electricity, they're clean. We've got to think of the whole life cycle here. Why are wind and solar in the mix today? How comes it's always wind and solar? People talk about wind and solar all the time. Well, you can see here, we start here, back in 2009, it cost over $350 per megawatt hour for solar. This has dropped down here to 50 by 2017. I can tell you now in 2021, this is more like 25 to 30. It has really come down in price. New materials have made them more effective. Wind has come down quite a lot as well. It was around 135, 140. It's now 45. You've seen here coal has actually gone up in price a lot. It's just more expensive to buy less stuff. It's also the fact that gas has helped, there's gases down at 60, displace coal. So wind and solar are now cheaper than coal and compete with natural gas. Geothermal range, and I say probable, it's hard to find these. A geothermal plant, let's back up. If I was putting in a 500 megawatt gas plant, I could tell you within a very narrow range how much it would cost. If I put a geothermal plant in some areas, it will cost more to produce electricity than if I put it in Iceland, say, at an event. The fuel is different, and this is what we're going to discuss. Now, there is an issue, and we mentioned it before. Wind and solar are intermittent. In technical terms, we say they're non-dispatchable. You can't just turn them on and off when you feel like it. The sun doesn't shine, you don't have solar. Another thing is of solar, of course, is they're mainly out in sunny areas. They're also dusty. If you have a big dust storm and dust is deposited all over the panels, then they can't produce as much power as they're designed for. Wind is, in Europe especially, there's a lot more offshore wind farms being developed. It's windier offshore, and you've just seen in the US that they're talking about building an offshore farm in the northeast. It's very windy. But if the wind isn't blowing, the sun isn't shining, then what do? Well, today you turn to coal, gas, or nuclear, or hydro if you're in that area. I'm afraid battery technology, although it is improving, compared to the first batteries ever made, I read somewhere, battery technology has improved the power it can hold and distribute, but only about 4 times for chemical batteries. And so any idea that, you know, whatever Tesla says, we're going to put lots of batteries in and solve the problem, it will be a very short-term solution, and they only last a couple of hours. So what other renewable energy sources are there? Which brings us on to geothermal. Now, it's a bit of a busy slide, and I will describe it and make it easy for you. But looking at solar and wind, okay? Solar costs about $1 million for every megawatt it creates. Wind, about $1.3 to $1.5 million for every megawatt it makes. Now that is comparable, if not, it's cheaper than coal, build a whole station. But here's a couple of issues with solar and wind that many people don't understand. The capacity factor is an average, if you like, of how much electricity or power it can create over time. Now, the sun may shine from 7 in the morning to 7 at night, but it's not always at its very height. In the early morning, late afternoon, it doesn't give the same energy. You have a cloudy day, it doesn't give the same energy. So we take the high point, nearly 30%. If you came to me and say, Paul, I need 1 megawatt of solar power, I'd have to install 3 megawatts so that on average you would get a megawatt. Now, that's fine, you can do that. Another thing is the footprint. It's about 60 acres or 5 to 6 acres save every megawatt. A similar geothermal plant will be in 5 acres or less and give you 10 megawatts. In Louisiana right now, the farmers are up in arms with the ideas from the state they want to have more solar because it's covering up the land. And if you're a farmer and your land is being taken off you, you can get upset. You can understand that. Now, wind has a better capacity factor. Roughly, if you need a megawatt, I'd have to install around 2 and a bit. But it does cover a far larger footprint. If windmills are too close to each other, they actually interfere with the wind flow, and the next windmill behind isn't as effective. So you have to put it a bit further back. Windmills are getting taller, and there's a good reason for that. If you go up, go and visit a city and go up a tall building, it's actually windier upstairs, so you make them taller. And as I said, they're actually putting more offshore where it's windier. But you still need a very large footprint. Another thing, as we said, if you look at this graph here and follow my pointer, wind, it tends to be stronger at night, but during the day it dips, so you have less power. Solar can only really make power in the day, but geothermal, like coal, gas and nuclear, just keeps giving you power. Now, the LCOE, by the way, that means the levelized cost of electricity. That's a way of standardizing things. It's like saying, how many dollars did you pay per square footage of house? It's a very common thing you say. The higher the LCOE, the more it costs for your electricity. And it costs a lot more to install, but it's very cheap to run. Another thing is, when we talk about capacity factors, it is greater than 95%. In fact, it could be higher than 95%. And it will deliver 24/7 for a long time, 25 plus years potentially. So what is it? When we talk about geothermal, it sounds great. It literally is heat within the earth. It comes from those two Greek words, geo, earth, and therm, heat. The thermometer, same word. And it's a renewable energy source because right in the middle of the earth, we have this inner core, which is about 10,800 Fahrenheit or 6,000 centigrade, which is hotter than the surface of the sun. And you can see here as you move up, things do cool down. But you know, you've seen it on the TV, you have volcanoes from time to time. Heat comes to the surface. Iceland is very volcanic, we'll mention that in a minute. You also go to places like Yellowstone. You see the geysers, very, very hot water. So not too far under our feet, depending on where you are, it could be anywhere between say 1,000 feet down to 10 or 15, 20,000 feet. It's a lot of heat energy. And for those of us who've worked in the oil industry, especially people like me who've also worked in offshore from time to time in a freezing North Sea, when the wind is blowing through those platforms and you wish you were somewhere else like the Sahara Desert, you can wrap yourself around one of the oil export lines and it is really hot. So there is a lot of heat. In fact, the Earth emits more heat every day. It could feed the Earth's electricity demands over twice as much. Worldwide, this might surprise you, US is the #1. As I said, mainly in California. There is a plant in California which produces well over 120 or 130 megawatts of electricity. That takes its power virtually from a direct steam source, which is very powerful. And there are other ones around which take it from hot water. Now, as it says here, the majority of the world's geothermal is near heat sources. If you look around here, you've probably heard of the Ring of Fire in the Pacific Ocean around here. There's a lot of volcanoes around here, earthquakes, very famous, San Francisco, of course, Mount Hood, up here, the volcanoes. So all around here, the Ring of Fire, there's a lot of heat near the surface. In New Zealand, you can go and watch it bubbling up from the surface in mud pools. Iceland is another area, strong volcanic activity. And in Europe, there's quite a few smaller plants. which are taking hot water out of the ground and using that. By the way, we'll come back, I'll show you this a picture of this in daytime. That's how small a plant can be. You could put a person next to that. The biggest thing is this area we'll discuss, but they're actually very small and emission free. What types and uses? In this blue box here is the kind of temperature range we're looking for to produce water from the ground. Anything over that, it's so hot it actually is steam, and you can use that steam directly as in a conventional power station to go straight to the turbine. I will explain why we're in this area, and I'll come back later on and show you the many other things you can do with geothermal aside from making electricity. This is what we are looking at as a company. We're looking at what's called sedimentary geothermal. I'm sure many of you here know the oil industry quite well, maybe working at, have parents or friends who are working at. A lot of the what's called conventional reservoirs we produce from, like sandstone, for example. If you put those under a microscope, they are full of holes. Anywhere between 15 to 20% of the rock you're looking at is empty. And that's what contains the oil, water, and gas. Now, what we're looking for isn't oil or gas, it's just the water. And at the depths they're at, they're very hot. These reservoirs are also what we call very permeable, which means the liquids can flow through them very, very easily indeed. So you don't need to frack it. It means, you need a lot of energy at the surface to pump water and chemicals down and sand to keep it apart. We know these reservoirs here very well. What we would do here is take the hot water out. It flows out the ground. It goes into your organic Rankine cycle plant, and the cooler water is injected back in. And through time, it makes its way back to the producing well, and as it heats up, and it comes back and it cycles. So you maintain the reservoir pressure. It doesn't cause earthquakes, a lot of people think. Yes, you can cause an earthquake if you inject water. We do understand the principles why. Any earthquakes I know of that actually have been created are so slight you would not actually know they were there unless you had sensitive equipment. So the technology I'll explain on the next page, called organic Rankine cycle, is what we are looking to use. We understand the reservoirs in Texas. We know where the hot ones are. We know how much they can produce in terms of hot water. That gives us a very good idea as to how much electricity they can generate. There are other sorts of geothermal systems. I've mentioned the ones that use direct steam. There's another one that's called enhanced geothermal system. This kind of rock is, it's not very permeable. It's what we call tight. It's hard rock. It can be very hot, but it won't flow. So you flow cold water into the rock and it thermally fractures. When the cold water hits the rock, it literally cracks. Imagine you have a piece of glass on a cold day and you pour hot water over it. If it's not Pyrex, it will shatter. And the idea is that you will connect these fractures to the producing well, and the water will then flow through the fractures, heat up and come back up again. Another experiment that's being looked at now is called closed loop systems, comes under the advanced geothermal system, where you actually do not flow any fluid out of the reservoir at all. You pump down a cool fluid. On the outside of the well bore here, the heat moves into the well. It heats up the fluid. You then use this hot fluid in your plant, like here, and it comes back down here and circulates. Now, this could be a wonderful thing. I know people who say this is the future. We know other people, some in researchers, who say, no, this won't work. But they're investigating it now. We know some people who are doing this. We wish them the best of luck. If you do have any questions, by the way, I can stop and answer them. Someone said, is geothermal energy centered around fault lines? The answer is yes, it can be. We can discuss that later on with the questions.
Yeah, Paul, I was going to hold them till the end if it's okay. And
Yeah, that's fine.
Okay.
Just a quick look. How is electricity generated, in case you don't know? They're called thermal plants because you're heating them up. Some people say they don't want nuclear because the electricity is nuclear. It's rubbish. Coal, gas, oil, nuclear, what it is, basically heats up water in a boiler, turns to steam. The steam drives the turbine, drives a generator, and that produces electricity to your home. So what's the difference? And there's a cooling tower. When the water comes back out, you've got to turn it back into water again to reheat it, to make it efficiently turn the turbine, water, steam, turbine, etc. It just goes around in a circle. I'll try my best to explain this. It's very simple, really. In the organic Rankine generation plant, the water from the reservoirs isn't hot enough to drive a turbine. But what you do, you go through, we call it an evaporator, regenerator, evaporator, and condenser. They're all heat exchangers. That's all it is. The heat is taken from the hot water into a fluid which is organic, like butane, pentane. It has a lower boiling point, which means that it will turn to the equivalent of steam at a lower temperature. That steam then drives the turbine, which drives a generator. The fluid is then taken back to the regenerator into the condenser and a heat sink. This is where the heat is taken out of it. And we'll see a picture in a minute showing you that most of the plant is actually taken up by taking the heat back out of the organic fluid. So again, it can be pumped back into the heat exchangers to be used again. There are over 450 of these plants in the world today producing electricity, and about 20 in the US. And it's been proven, and technology is improving all the time. Another thing is, we talk about the reservoir, but other heat sources are viable. This technology is used a lot. You may have heard of people who are taking wasted heat energy up flues or chimneys in factories and turning it into power. They use organic Rankine cycle. Instead of hot water from a reservoir, they use hot flue gases in the heat exchanger, heat up the fluid and drive turbines. So this technology, it comes after a guy called Rankine, believe it or not, Scottish guy who died around 1870, 1880. This isn't new physical theory. While I'm here though, I just want to give you some idea of how much energy is in water. 1 litre of water, which is about 1.7 pints, okay? If you take energy out of that 1 litre of water such that it drops its temperature by 1 degree centigrade, you have taken out 4,200 joules. That is 4.2 kilowatts. So if I flowed 100 litres every second and dropped the temperature by 1 degree, I've taken out 0.4 megawatts. If I can drop that temperature by 50 degrees, all of that energy, I have taken out 21 megawatts. Now you can understand why hurricanes are so powerful. It doesn't take much of a temperature drop in the water to release lots of energy. Unfortunately, the OIC plant isn't 100% efficient and it's not all turned into power, but water contains a lot of energy. Just remember that. What do they look like when they're built? Well, there's your well, there's a separator, goes into the heat exchanger, through the turbine, and all of these are to cool it off through recycle, if you like, goes back round. The organic fluid goes back round here, and it just repeats. Instead of water steam, it's an organic steam. And that's what it looks like. Brand new shining plants. This one is in Germany, Kirchstochach, which is my terrible German. This produces 5.6 megawatts. It's quite a small plant. Water temperature is 138 degrees centigrade, which is around near enough 300 Fahrenheit. The size of that, if you look at a football field, it's 1.1 acres, okay? That would fit on a football field plus. That you're seeing is probably 1.5 acres at best. Right next to a forest, and no one is worrying about the quality of those trees because it is emission free. That would 5.6 megawatts If that was the US, that would be around 3,500 houses. In Germany, that would probably feed a town 5,000 or 6,000 people. So we're talking about this bit here, binary geothermal power plants, 200 Fahrenheit to 350, around 100 degrees C up to say 200. Look at all the other things you can do. Around here, for example, they're doing this a lot in Germany and Iceland. You take the hot water and you pipe it to houses and you can heat the house up. But look at all these as well. Onion and garlic drying, food processing, lumber drying, soft drink carbonization, geothermal heat pumps. People are talking about this a lot recently, about new houses being built and taking the heat on the wall from the earth from your own backyard. So there is a lot of stuff you can do with geothermal. You don't just have to turn it into electricity. You may have what's called dual plants where you create electricity and also send the water to district heating. In Iceland, it's a very hot place. Almost every building in the country is heated by hot spring water, and more than 50% of its power is from geothermal sources. They are wisely using something that's been handed to them free. One of the issues we have with electricity outside of things like hydro, you can fill up your dam, you are storing energy. But you can't store energy from solar, for example, very easily. The batteries we spoke about, they can hold a charge for a couple of hours, and they don't give out as much energy as you need. The whole city of Houston, you need thousands of batteries and you drain them very quickly. But I just told you that water contains a lot of energy. What we find sometimes in some parts of the country, wind in Colorado, wind and solar in Texas, is that they can generate so much electricity, it can't be used. And what happens is that the authorities will then give them very low pricing or even negative pricing. They're trying to dissuade them from putting their power into the grid. What you're seeing here, you can go on ERCOT Live, is a live real-time map. This was October the 25th, 5:45 at night, of the spot prices of electricity. And down here in this bit, it's not negative, but it's far lower than this. Sometimes it's negative. If you could take that power, literally while it's free, and heat up the water as you pump it back into the ground, that energy would be stored for later use. You could make your reservoir even perhaps hotter than it was to begin with. At least you could maintain power. But because it's already down in a very hot environment, it will not lose that energy very quickly. And when you need it, you can tap it and use it. This is what we call an earth battery idea. And it's something we like to look into further. There's a few facts about geothermal. They're the same environmental considerations as the oil and gas sector. The oil and gas sector is subject to many laws about the environment. Whatever you might think that you heard in Congress today, Derek, Gus, we've all worked in it. I'm very proud to work with companies actually who do take it seriously. In places like Texas, you need to drill wells, of course, for geothermal, land. All these laws exist. It's not as if we're going off to the government and saying, hey, we want to try something different and waiting years for them to understand it. I don't know how many wells have been drilled in Texas. I wouldn't even like to hazard a guess, but it's going to be probably 1 million plus. And we know very well now how to protect ground drinking water and stuff. Very, very strict on that. Another thing about geothermal, we said no emissions. Now you may remember looking back at the coal-powered fire station, I didn't mention that at the time. One of the byproducts isn't just carbon sulfur, it's ash. When you finish burning coal, it hasn't completely disappeared, has it? You have lots of sludge left, lots of bits of burnt coal. You have to dispose of that. Again, with geothermal, you don't have to do that. And it will meet all the federal, state, and local clean air, water and noise control regulations. These plants are almost silent. There's not many, the only moving part really is the turbine, and that's going to be in a box. You don't hear it. So where do we find these geothermal resources? The map on the left is temperatures that we know of at 5.5 kilometers. Well, that one out there, 5,500 meters. This is about 18,000 feet. That is quite deep. You'll notice that all the warm colors, the oranges, yellows, reds, fall around here in the west, but there's a big swathe right through here in the Gulf Coast of Texas and a little bit up in West Virginia. This map here, which looks like a rash, these are wells with bottom hole temperatures greater than 120 degrees centigrade, which is low side of the temperature you need to start making geothermal work. It says greater. Some of these will be 180, 200. You can also see that Texas is awash with data. Look at the data here, the points, everything. This is the Marcellus is over here. This is the Bakken, the Permian Basin. The amount of wells drilled here is phenomenal. We do have a lot of information to tell us about these reservoirs, and that's very important, which we'll see why. You're going to say, why are there so few geothermal plants today? Well, the cost of geothermal is quite expensive when you compare it to conventional. So unless it is situated right next to a hot spring or steam vent, or someone asked about faulting, yes, faults can transmit steam to the surface. The energy of the steam vents is substantially higher than water. If I remember rightly, you can get 4,200 joules out of a litre of water at 1 degree drop. If you turn that into steam, it's like 2.6 million joules. There's a lot of energy in steam. And thanks to fracking, you know, natural gas is, when I was here, it was around 2009, 10, natural gas was going up to $11 to $12 per 1,000 cubic feet or 1,000 BTUs. It dropped down to less than $1 a few years back. It's rising again now to around 4 or 5, but it's a lot cheaper than it would have been without fracking. The other thing is that gas emissions are about 40% out of coal. So it's called a displacement fuel. It got cheap enough to say it's cheaper than coal. And fortunately as well, it's also a lot cleaner, but it's not fully clean, is it? And so there's enough electricity being generated. You can see here on this map, around 2007-8, coal, the bars start getting smaller as natural gas starts coming up. Let's see who's listening. The government wants to reach 50% of emissions in 2035, compared to what reference year?
2005.
It's the right answer. Why do you think? Be careful with politicians, people, of whatever persuasion. This was the peak of US emissions. Thanks to fracking and other things, other outsourcing of industry, the emissions have come down. So when the government say we're going to halve our emissions by 2005 to 35, you can come out here in a straight line almost and say, yeah, you could do that. If they said they do it from today, that's a bigger order. So be a little cynical when people say things and check. But US emissions are dropping quite a lot at the moment. Another thing about geothermal, this is an issue many investors seen or have seen in the past. If you don't know what's there, like in oil and gas, you need to explore. You need a pre-survey and exploration. This normally involves seismic, understanding all the squiggly lines people like Derek look at, saying this looks like an area we could explore in, drilling a well at great expense, testing, and so on. And then you decide, do I have enough resource to develop this oil field? In places like Texas, though, with so many wells drilled, in the vast majority of cases, we can eliminate these costs because we have the information. As I said, millions of wells, hundreds of thousands of data points in the Texas Railroad Commission, telling you a lot about the permeability, the rock type, the temperature, the flow rates, all of these things that you used to spend millions and millions of dollars on, you don't have to. Our task is to reduce these costs, the well field development. Geothermal plants cost you whatever the geothermal plant cost you for that rating, say 10 megawatts, 20 megawatts. But depending on the quality of the resource will depend on the number of wells you need to drill. The fewer wells you need to drill, the cheaper it is, the cheaper electricity. That's the challenge we're facing. And one of the things, the advantages about the oil and gas industry is that there are many people with this kind of experience now moving into this sphere. So what else is changing now? Well, we're all seeing it. We just discussed the gas emissions. Google carbon free by 2030. The EU wants to be carbon neutral by 2050. GM, like Ford, have just announced they're going to spend billions of dollars on electric vehicle production. ExxonMobil, these three activists recently, are trying to stop a development of the west coast of Africa. Like you've seen here on the bottom right, Goldman Sachs, they're one of many large investors who are starting to say, look, we're not going to fund oil and gas exploration anymore. So they're looking for other forms of investment. There's many things you can invest in, obviously, but energy use in the developed and developing world is something that is set to increase. And if we're going to do this successfully and keep our planet not from warming too much, we need to look at alternatives. And they are looking now to invest in greener fuels. Solar and wind, we've seen, have already had lots of investment. We think geothermal is going to be the next. Another thing is how prices drop. If demand goes up and people want more, people tend to manufacture more. And as they manufacture more and get more efficient at it, the prices drop. That's an example of solar. Utility tracking, by the way, is expensive solar. That's where it follows the sun. But, you know, don't worry about what it says, all the three types there. But the fact is the costs are coming down. Airlines, the Comet 4 actually wasn't the first jet airline. It was the Comet 1. It suffered a series of accidents. But, you know, even going back to the year 2000, this is a common one to show. Fuel consumption. There are more people on the plane. It's cheaper to fly. It's cheaper to do lots of things. You could say the same for a TV. I just pull this one up. It's household refrigeration. The volume is going up, the energy consumption is coming down, and the cost is coming down over time. And you could probably look at many things. 100 years ago, most people listening in here probably couldn't afford a car. Now, we're a 4-car family now. Things are getting cheaper. And we believe the same thing would happen in geothermal, is if we can start this off, us and other people, is that the people who make the plants will be able to drop their prices, and therefore it will become cheaper to develop, the same as other energy we've seen like solar. But renewables of all kinds, you know, they do have a bit of an issue today, and that issue is it depends on your location. You've seen this map already. This is the map. By the way, does anyone know what this little dot is here?
Yellowstone.
Yellowstone, yes. This would be the perfect place to put a geothermal plant. I don't know if you've been there, I have. It's one of the most amazing places. I've been to over 45 countries. This is one of my favorite places. Keep it pristine, but it's a great example of energy coming to the surface that can be used if you so wanted to. Okay, if we're in the solar business, you look at this map, voltaic solar resources. As you can see, the Southwest Texas, New Mexico, Arizona into Southern California, Utah, have a lot of sun hours. This is in kilowatt hours per meter squared per day. And it goes up quite a lot. The sun gives a lot of energy. Anyone like me knows if you stand out too long, I turn into this color. But if you're up here, you can still put solar in, just expect it to be generating the same kind of power as this does. Wind. Remember, I showed you where all the power stations were, and I might have mentioned there's a whole swathe of wind generation through here. Well, here's why. This is the mean annual wind speed at 80 meters. It has to be off the ground. And so when people say, oh yeah, the politicians like to take credit for things, we've got a lot of wind. If I was going to spend $1 million on a windmill, I'd rather put it up here and generate twice the power as putting it in here. The reason you have wind here and solar here and geothermal in some of these areas is that's where the resource allows it. If you're up here, you don't get much sun, you don't get much wind, and you get much temperature. So you could easily put a gas or coal power station there. This is the challenge we're facing. I don't want to give anyone the impression that, hey, we've got the solutions and it's easy to solve. There are challenges involved. But up here though, this area, offshore, you get a lot of wind. And this is why they're putting the wind farms in here. If you fly from Paris or Amsterdam to Aberdeen in Scotland, you'll go over what's called the Dogger Bank of Essex, which is the east coast of England. You'll see hundreds and hundreds of windmills. And Scotland has just signed an agreement to build the largest wind farm offshore Aberdeen in the northwest of Scotland. I lived in Scotland for years. My wife comes from there. I can tell you it's a pretty cold, windy place sometimes. They will get a lot of energy. But in places where geothermal, solar or wind isn't as effective, it becomes more challenging. This doesn't mean you can't put windmills here, by the way. You can. They're just not as efficient as through here. So you would need more of them. Any idea where you would find this place? Does the architecture not give it away a little bit? Okay, we'll move on. I'll tell you, it's in Germany. It's a beautiful place. My brother lives very close to here, actually. It's in southwest Germany. Sorry, southeast Germany. It's a beautiful part of the world. I recommend you go there. A place called Holzkirchen, or High Church. Little town, green around, it's beautiful trees. There's lots of trees down there. And there's something here that looks quite interesting, though. I feel like a spy. You zoom in and it's getting a bit more suspicious. Must be a CIA plant. Actually, no, it's a geothermal plant just on the outskirts of the city. Hidden behind the trees and the berm here. Most people there probably don't even know that the majority of their power comes from a geothermal source, which quite frankly is placed next to where they live or where their kids go. Now you won't guess where this is. I'll tell you it's also in Germany. That is a geothermal plant. This one, I believe, is a drill that produces power and it sends hot water out to most of the residences. You look at that, that looks quite modern art to me. I like the look of that. Would you mind living next door to that? Because actually it's in the suburbs of Munich, one of the largest towns in Germany, right here. And it's next to what's called a gymnasium, which has nothing to do with exercise in Germany. It means high school. The Freien High School, there is a geothermal plant right next to it. Now, why am I saying this? Because as I said many times, emission-free, almost silent. If you had the resource in the outskirts or even in the middle of a town, you could put a plant there, you could disguise it as a modern art museum and no one would know. And just to let you know, around here, there is a gas-powered plant which recycles a lot of its waste. Next to it is a geothermal plant, almost in the center of Munich, which is feeding 80,000 people with hot water for district heating. Really last question. How can we all play our part? What is it we have to do to make the future cleaner? No one? I'll take a guess. Let me show you this. Stayed in a hotel the other week, 65 degrees. I don't know the last time anyone was in that hotel. It was 95 degrees outside in the shade. Felt like 105. The chances are, realistically, you could have set that to 70, 75. Save energy as well. Remember I initially said you go out, you've left the light on, do you worry about it? No, energy is cheap. And we tend to forget that it's generated somewhere. Replace these with these. They use up a lot less power. I'm going around my house doing so right now. We're all responsible for the part here. Don't look to government or industry all the time. Look at yourselves as well. You don't need to buy an F-150. If you do, fine, but you could buy something smaller. And the passing thought is, how many planet Earths do we need to provide resources we're using? Well, I got this from a website. I'm sure you can find different numbers. But at this moment, according to this particular website, we need nearly 1.8 planet Earths to provide the resources for our annual use of all types of energy, which is completely unsustainable, and which is why we need to move to renewables very quickly. So to summarize, we are at a tipping point. In Scotland next week, the leaders will get together again and start hammering out ideas as to how we can keep the Earth to 2 degrees or so warming. And this is going to take engagement and promises from all stakeholders. And at the end, I say us. We also have to play our part in using less energy. Ever since the pandemic, it's been getting better, actually. The public is speaking up now. There is more demand for emission-free generation. And you've seen businesses, I mentioned Google, Amazon's the same, Microsoft, they're all saying that they're going to become carbon neutral by 2030, 2035. And investors aren't giving money to people who aren't going to do something about their emissions. We've seen wind and solar make significant improvement. You may remember that solar generation is set to increase substantially, but they're not capable of providing power 24 hours a day, which is what we all demand. Battery storage technology, it is improving. But, you know, despite years of research, it hasn't improved enough. I mentioned the Earth battery idea. I told you how much energy water actually contains. Heat water up, put millions and millions and millions of liters, barrels, whatever your measurement is in the ground, and you can store a lot of energy. Finally, as we said, geothermal is emission-free, can run 24 hours a day. It's a very small footprint. It can be placed very close to residential areas. And it can be used for many things other than power generation. With that, I'd like to thank you very much, and I'll leave you a picture of the world's largest binary plant in New Zealand. That is steam, don't worry about it. If that was a solar plant, you would have had to have cut down all of those trees in the background. 82 megawatts. Okay, thank you very much indeed. Any questions now? We'll open up to the floor. Any we can't answer, by the way, if you take down our details and email us, we'll answer you that way.
Thanks so much, Paul. Carolyn, if you want to say anything. First, I was going to go through, we have quite a few questions, and I was going to ask Paul to address. I said, going back to from the start, he said, Mark says that everything I read about or see about renewable energy talks about the cost of fuels and facilities, et cetera. But what about the full life cost, including waste disposal? And by that, he means batteries and spent turbines and things like that. Is that factored into those costs?
The full life cost of geothermal, the vast majority of costs are up front, and that's installing the plant and drilling the wells. In terms of emissions, very, very small. Turbines, what they're made out of, I'm sure they can even be recycled, but if you have a decent maintenance plan in place, you don't expect things to break so often. We were talking to someone who developed geothermal plants in Oregon, and he had a very good maintenance plan, and he managed to keep his plants going. But the question is very valid because, and I want to leave you with this as well, you don't get something for nothing, okay? If you bought an electric vehicle, from the moment you drive it out of the shop, it produces far less emissions than a standard car. But making it is not emission free, and digging lithium out the ground and so on and so forth, there is a cost to that too. So the full life costs are far less than oil and gas or coal. How much they cost in the end, I don't have an exact answer, but compared again to say coal, where you're getting rid of all the residue from the burnt coal, we don't have residue in geothermal. The water is pumped back into the ground.
I wanted to, since you mentioned that now, I wanted to ask about the, I have been in the water business, but I don't know about depths that you're talking about.
Mm-hmm.
So that's not artesian. Does one have to pump that up to the surface, those hot waters, and then pushing it back down? Does that take energy?
That's an electric pump.
Okay.
The pumps, most of the pumps I know I had in the oil industry for water injection run off electricity. Of course, the power generation on the platform was natural gas. The water you use from the depths, generally, I'll say, the water you use for the energy you require are mainly around, I would say, and Derek can jump in here in geology, 8 to 10, 12,000 feet deeper, way deeper than the artesian water, you know, and the wells would be cemented off and cased off. They wouldn't touch it at all. Some places, again, you know, like we mentioned Iceland, you can see it in Yellowstone. In parts of California, the steam comes right up to the ground through vents and you can tap into it there. It's probably not the kind of water you would like to drink straight away. It'd be very saline. Water at depth contains a lot of salt, and it may also contain other nasties that you'd have to knock out. Derek, have you ideas of the kind of depth ranges, especially in Texas?
Where's the camera? Right. Hello. You know, it's going to depend. It's going to depend on the reservoir, but you know, 10,000 feet probably on the low end, and then you know you get over even into Louisiana and you're as deep as 20,000 feet. But again, it depends on the reservoir you're targeting. But the numbers Paul's talking about is pretty much right in there, 10, 12,000.
We, you know, in our area here, you know, the deepest we know about water is the Catahoula, and you know it's very, very salty at this point. So the next question is you mentioned, you started to talk a little bit about the fault line. This one mentions I-35, but is that indicative of the heat, or is that just coincidental, or how does that work?
Again, it's one of those, you always get this from engineers and geologists. It depends. In some areas of the world, faults indicate tectonic activity, and tectonic activity means a lot of energy, which means heating up water. In other parts, the energy isn't so great, and they don't necessarily indicate that you have hot water or something you can use. Again, that's a question. Derek, is that good enough?
Yeah, I mean,
Derek's our geologist, by the way.
So where you are in the world is going to depend on what you're targeting. So down here in the Gulf Coast, we've got reservoirs as a conduit for circulating the hot fluids. If you're up in a place where you don't have a sedimentary basin, where you don't have a lot of sediments, you have, say, you know, basalts or lava or granite, or you know, some kind of volcanic rock or igneous rock. You're often relying on those faults to provide the permeability pathways to circulate the fluids, and so you often do target those faults. Yeah, for geothermal.
Thank you. Drew asked, I said, I'm not sure, it might be jumping ahead in this technology. Is this technology a better way to cool your house and use less electricity to cool your home? And I'm assuming that we know that, like you said, Iceland and other people use it to heat their homes, but I would think that to cool it, it just means it's a cheaper way or use less energy if you use this. It depends on how you generate the electricity, I guess.
Water at this depth is hot and is better for heating. Of course, it produces power, which you can use for air conditioning units. But you also have geothermal pump technology, which you talk nowadays. And that comes from burying pipes quite shallow in the ground. In the winter months, the ground is warmer than surrounding air, so it provides some warmth. In the summer months, it's cooler than surrounding air, so it provides some cooling. The kind of energy we're talking about is greater than that. I think that's what they're talking about, called geothermal pumps.
Yeah, I mean, geothermal really is kind of three things. You can make electricity, you can use it for heat, and then you can use it for sort of HVAC, for heating and cooling. And you know, for power, you're talking about deep hot water, and for direct use heating. You know, for that, you know, there was that slide that Paul had with all the kind of the many different sort of uses of geothermal. And then there's sort of the residential scale, where you're relying on really the ground, the shallow ground, as your heat exchanger, because average ground temperature, at least here in Texas, is 71 degrees Fahrenheit. And so, you know, 70, if you can get 71 all year, that's actually pretty nice to either heat in the winter or cool in the summer. Up north, obviously, it's cooler. The average ground temperature is cooler. And so, you know, you're essentially, in all of the systems, you're circulating a fluid to exchange heat from one place to another. And so it just depends on how much energy really you need.
Thank you. Mark asked about, and could oil and gas wells that have been plugged and abandoned and repurposed or rehabilitated for water production? And I know a lot of times here, we have from time to time people in this area that want to use those wells for injection purposes.
Mhm.
But would there be any use for these in water exploration?
And the answer to that, of course, it depends, which was my favorite answer tonight. Yes, we are discussing that, and we are talking to people about how we could reuse them. I just want people to be aware that depending on the age, depending on how they were constructed, you may not want to touch them with a barge pole, because they could be more hassle than they're worth. You know, I've come across this in my experience.
I agree, and I agree with that. I guess you know, one thing about it is they pass through a lot of drinking water aquifers on their way up and down. And so the integrity of that well has got to be considered so that you don't spill off into the aquifer that our drinking water supplies.
Oh yeah, of course. The other thing, of course, is, you know, even if that is protected, you might find that certain things are stuck in a hole, or down hole is rusted a bit, or something has happened, and you just can't fix it, and you're just basically wasting time and money on doing something that you shouldn't have touched in the first place. So the answer is yes, we are hopeful that it could be some wells we could repurpose, but there will be many wells you really shouldn't touch.
A few more here. Water saturated sedimentary rocks in the Gulf Coast warm trend are pretty good insulators. How rapidly will there be thermal withdrawal, drawdown for wells in this trend until you lose your temperature differences for an advanced cycle installation?
Yeah.
I don't know who Jim is, but
it's a very good question. So it's an excellent question. And again, it's going to depend on your reservoir. How much volume are you taking out? How much are you putting back? How far apart are the injectors to the producers? What is the temperature? What is the thermal capacity? One thing for certain is that unless you have what we call infinite acting aquifers, which are at the right temperature to keep pulling fluid in, as you put cooler fluids in, naturally you will drop some temperature. From a subsurface and reservoir engineering perspective, your target is to put in as few wells as possible. Derek and I discussed this not so long ago, and we said, look, from a reservoir engineering perspective, when you're developing an oil field and you're putting a water injector in to push the oil to the producers, you're trying your best to understand where the best place to put the injector is so you can avoid producing as much water or delay what we call water breakthrough. If you think of hot water as oil and you injected water as a standard injector, you try to identify the reservoir or understand the reservoir enough to stop that cooler water reaching the producers quickly and allowing more residence time in the reservoir to warm up. Now, the larger the reservoir, and obviously the deeper it is, the more that will happen, the less heat you will lose. But yes, you would be expecting to lose some heat. That would have to be investigated on a case-by-case basis. So if you thought, for an example, you could produce 15 megawatts from day one, and you put in a 15 megawatt plant, you might find in 5 years you can only produce 11 or 12. So what you would have to do is understand that potential energy drop and size your plant accordingly so you don't have an immediate drop in power. It's an excellent question, and it's something that all I can tell you is you would have to investigate that on a case-by-case basis.
one thing that before you would undertake any kind of, I guess you could say large capital expense in a project is you got to do a feasibility study. So you need to collect all the information that's available and really do your homework. So as Paul said, do some modeling, try to image the aquifer. Is there seismic available? Understand the connectivity. How big is that aquifer? Make sure you're not going to draw it down, as you say. So yeah, but before you even drill a well or build a power plant, you should have a really good idea of how that's going to behave.
That's right. And mitigation plans, that if your temperature does drop more than expected, then where's my backup well location? You try to avoid that, of course, because it's additional cost, but you should always have an alternative in your back pocket so that you can keep on progressing.
Okay. I think the last question, or next to last, Larry asked about, I guess, still hydrogen sulfide, H2S. There are
Yes.
some emission considerations. Our largest hydrogen sulfide account in the world has a geothermal plant. The water picks up silica and H2S when it is pumped into some formations. So I guess I'm assuming, Larry, when it comes to the surface, we're talking about.
Yeah, it's mostly a problem if the hydrogen sulfide causes corrosion in a leak.
Yes, yeah. I've had H2S issues in fields I've worked in. Of course, not all fields are H2S. Don't produce it. You can, one of the things you'd be doing, it's not just looking at reservoir and geology. You have an assay of the water, take a PVT, understand the chances of creating H2S, let alone producing it. You can put scavenger in. Some geothermal plants, I think they're called an expansion one, steam expansion. They usually vent straight to the atmosphere. ORC doesn't. And in some of those, if you produce the nasties up with the water, you can vent that straight into the atmosphere, which is what we wouldn't do. But yeah, you're right. I mean, there's no silver bullet. Sometimes, depending on the temperature drop and the pressures you have, you may precipitate scales and things like that as well. So like in the oil industry, we may have to be putting some sort of chemical injection to stop this happening, or some kind of filtration. Definitely, we will be taking lots of samples for PVT analysis beforehand, so we know how to plan ahead.
I think that's it. I do have one personal question, Paul. My mother and family still, my mother's passed, but a lot of my family's still in Lancashire, Blackpool, and I wondered what part. I noticed the University of Sussex. Are you from down there or far up north?
Yeah, I actually come from North London. Sussex is on the south coast, Brighton. I used to go out with a girl many years ago who came from a place called Preston in Lancashire. Feelings for her, but that was a long time ago. So yes, Lancashire is just north of Liverpool, which of course is famous for the Beatles, and some beautiful parts of the world up there.
Well, yeah, Preston is on the way to Scotland on the train from London, and you take a left and go to Blackpool. That's where my mother was from.
All right. Yeah, I've been to Blackpool a few times. They have a large pleasure beach there, fun fair. It's
anyway, I thank you so much. I was just curious, and thank you for so many, such a good program. I said, I don't know, Deborah, you want to come back, or do you want me to talk about next month, or?
Yeah, take it away, Paul, with what's planned in November.
One thing I just want to interject before you close out.
Please do.
If anyone does have any questions, and again, not business related, but if you have any technical questions or you're interested, just feel free to email any of us, and we'll be happy to have a chat.
Of course we would.
Appreciate it. And questions always do come up when you turn the computer off. So we'll do that and follow up if anybody has questions and share them. So thanks again. Really, really enjoyed it. Learned a whole lot. I just wanted to, sorry.
I'll put the screen back to you, I believe.
That's okay. Yeah, you can. But I just, mine is just to announce that this, this is a monthly meeting that we have between September and May, and next month in November, the 18th at 7 o'clock, same channel, November 18th, Thursday. Dr. Erin Kennedy is with HARC, which is Houston Advanced Research Center. She's going to update the State of the Bay, the annual report card that they do with the TCEQ and others. So again, it's just the State of the Bay. We give grades on anything from plastic bags to bacteria counts and things like that. So they give an A, B, C, and D grade. So far, it's holding pretty good, but obviously every year it's such an important bay system, both ecologically, commercially, and certainly a place for people to go recreate. So I always want to stress that what we do here in the Woodlands and what we put in Spring Creek ends up in that bay. So she's also going to talk about the things we can do to help preserve the quality of that. So that's November the 18th, 7 o'clock. That's all I have. Want to go, Deborah?
Yes, I just asked Derek to add his email and he's done so on chat. So all those technical questions are going to come up later today, tomorrow. Derek's been gracious to offer us that his email. So I think we're close to a wrap. Any other chats, any other questions before we sign off tonight?
Oh, Deborah, I want to mention, I don't know if you did, but we're now recording these each time and they're going to be available. You can go back to that, to our YouTube channel or whatever, but you can find that on the website, right? So this will appear after John can get it done. So it'll be something we can go back or you can send to your favorite friends and educate them.
And we've had quite a reach when people have reached out to us after seeing the recordings. Very thankful that, yeah, John Geiger set that up with YouTube from other states, especially that they've been reaching our recordings. So on that note, thanks to EarthBridge, they've done a great job tonight informing us about geothermal, and I'm sure more questions will pop up. Be sure to email Derek with those. And thanks to Carolyn Newman, who put this all together, and our live for the first time remote setting at the coffee shop has been great for those of us here enjoying her brownies and coffee. For that, we'll sign off on Thursday night, unless there's anybody else. All right, good night, everybody.
Thank you.
Thank you. Good night.
Thank you.